Hello and welcome to today's session. We're looking at gravitational fields, and there are three learning objectives for today. To understand what we mean by gravity, to understand how we represent a gravitational field, and to look at radial and uniform fields. So there are three questions on the board. What can you remember from your early physics career? So three questions. What sort of objects cause gravity? What does an object need to cause gravity? And if we consider gravity on a planet, which direction does the force of gravity act? So have about 30 seconds to think about that. Okay, with the first question, what sort of objects cause gravity? So anything that has mass, so any object that has mass will cause a gravitational field around it. So anything that has mass has a gravitational field around it, and there's a force due to gravity between two objects if they have mass. That leads into the second one. So an object needs mass to cause gravity. And the third one, if we consider gravity on a planet, which direction does the force of gravity act? So the force of gravity between two objects is equal and opposite. So if we consider the planet, it's going to act towards the center of the planet if you've got an object on the surface. If you think about a coin, so if you think about dropping a coin, you observe the coin falling to the earth, and we do not notice that the earth is being attracted towards the coin. We observe the coin falling towards the earth. So due to the size of the masses involved. Okay, so we've shown that anything that has mass has a force due to gravity. And the larger the mass of the object, the greater the force due to gravity. So larger mass objects have a greater gravitational pull. We can represent gravitational field lines thinking about the path an object will take. So dropping an object in free fall. I talked about dropping a coin earlier. If you drop a coin, it's going to fall due to gravity, and it's falling on what we call its gravitational field line of the Earth, or the line of force. And for a planet, they're directed at the center at all points, so we call this a radial field. So the force due to gravity, we can represent the force acting towards the center of the mass. This radial field at strength varies with distance. So the further you are away from the object, the size of the force decreases. It's actually an example of an inverse square law relationship. So the gravitational force is proportional to 1 over the distance or separation squared. Inverse square laws come up quite a lot in physics, so you'll see it in electric fields as well, and for radiation as well. So for gamma radiation, there's a required practical where you investigate gamma radiation and look at the inverse square law relationship. So we consider two types of field pattern. The radial field, which you saw in the previous slide, which is like the spokes of a wheel and act towards the center, and a uniform field. So Uniform being that it's the same. So it's the same direction and magnitude everywhere in the field. And we can represent the uniform field in terms of a picture. So you'd have equally spaced parallel lines. So we've got two types of fields. What sort of field do you think the Earth has? So if we consider the force, the gravitational force acting on a small object on Earth, the strength of the force decreases with distance. So the gravitational field strength decreases in the same way. So we've got a radial pattern. But over small distances, we can consider the field to be uniform. So that change is insignificant. So very small relative to the radius of the Earth, we consider it to be uniform, and we use a value of 9.81 meters per second squared, or newtons per kilogram. And if you think about the altitude, so if you run a calculation, at 100 meters compared to the surface, the strength of the gravitational field of the Earth is smaller than at the surface, but it's generally too small to be considered in the calculations that we'll do. So thinking of the gravitational field strength, we can define it as the force per unit mass. So for a mass on Earth, a small mass m on Earth, we could define it as G, which is the strength of the gravitational field, is equal to the force per unit mass. So F would be the gravitational force, m is the mass of the object. So A level, we consider it to be 9.81. G is a value of 9.81, and the units, derived units, would be newtons per kilogram. So as I said in the previous slide, we can have G as newtons per kilogram, or we can define it in terms of an acceleration, and we'll look at that on the next slide. So we can consider an object in free fall, so falling freely under its weight, which is a force due to gravity. And doing it this way, we can define the gravitational field strength in terms of an acceleration. So imagine an object's falling, we've dropped it from rest, it's falling to the ground. From Newton's second law, we know the force is equal to the mass times the acceleration. So we can rearrange that to get the acceleration, which is force over mass. Previously, we'd shown that you can have the force equaling to mg, because remember, g is equal to F over m, so the force is equal to mg. Substitute that into this relationship, so you get the acceleration is equal to the mass times g over m. Those m's will cancel out, and you'll be left with the acceleration equal to g. So an object in free fall will fall with acceleration g, and that's independent of its mass. So if it's dropped in free fall, it will fall with g, which is 9.81 meters per second squared. So we can have g with two descriptions, units of newtons per kilogram or meters per second squared. And if you look at your data sheet or formula sheet, you will see both are on there. Okay, so let's try a simple question, just putting a few of the concepts that we've looked at. So the gravitational field strength on the surface of the moon is 1.6 newtons per kilogram, what is the weight of an astronaut of mass 80 kilograms standing on the surface of the moon? So we need to be able to find the weight, the force, which is the weight is equal to the mass times g. So this force is the weight, so it's a mass times g. So all we need to do is substitute the values in. We've got 80 kilograms, we've got a gravitational field strength of 1.6 newtons per kilogram. Simple calculation for this one, because you're given the acceleration due to gravity, or the gravitational field strength, so 80 times 1.6 gives us 128 newtons. We need this to two significant figures, so that's just 130 newtons.